Today we are going to do 10.3 of our chapter 10.3, that is the Boltzmann distribution. Okay, till now in our last lecture, we know that we discussed about the catalyst. We were discussing about the reaction rate and equilibrium. In our last lecture, we discussed about how catalysts help in increasing the rate of reaction or in equilibrium and all. Okay, now today we are going to discuss about the Boltzmann distribution. Okay, now the energy of moving particles. We learned in our previous classes that molecules in a gas move at a very high speed, colliding with each other with the walls of the container they are held in. Suppose this is a container, okay, and it's closed container, and the gas particles are there in it. Now, gas particles have a tendency to move here and there, and that motion of gas particles to move here and there is known as Brownian motion. Okay, they collide with not only with each other, they also collide with the wall of the container. And as they collide with the wall of container, they create pressure on the walls. That is what we call it the gas pressure. So these collisions are said to be elastic. It means there is no loss of energy into it. They are perfectly elastic collisions, and the molecules do not slow down as a result of collision, and no energy is lost. So it means that whenever they collide with each other, no energy is lost, and they never slow down. The speed of their collision and everything remain constant. Okay. Now, in a gas, a liquid, or a solution, some molecules move slowly with low energy, and some molecules very fast with very high energy. And most of the molecules move close to the average speed and have close to average energy. Now, as we all know that some of the molecules are very fast, some are a little bit slow, but some of them move with an average speed and they have some sort of, you can say, average energy. This spread of molecular energy in gases is known as Boltzmann distribution. And the graph is marked with the line EA. Now, if you see the number of molecules with a given energy, and the energy. Now, suppose if I say energy, this much amount of energy, only this. If I say this point, so it means this much amount of energy is there. Now, number of molecules here, this much amount of energy is this. So, in a similar way, you can distribute the different energy. Now, suppose this is energy EA. Now, this energy EA represents the activation energy of a reaction. So activation energy means the energy which is required to activate the reaction. There's a certain amount of energy required to proceed the reaction. So the graph is marked with a line EA that represents the activation energy of a reaction. You can see from the shaded area that only a small portion of a molecule have more energy than EA. Now, if this EA is the activation energy, and only very small portion of particles, they have energy more than EA. Clear? That is enough energy to react. So only small portion of the particles have sufficient amount of energy so that they do react. Clear?
So I don't understand the graph. Like
which one?
The line going up and down.
This is simple, the energy. It's a simple energy distribution. As the energy is increasing, number of particles, it is number of particles with the energy.
So energy.
Means energy of particles. Suppose there are 10 particles. Fine. This is a container in which there are 10 particles. Fine. Okay.
Yeah.
Now some particle is having this much amount of energy, some particles have this much amount of energy, some particles having this much amount of energy. So every particle will have different energy.
Yeah.
Here, so this is the graph of that thing. Now, for a particular reaction to occur, we require some sort of activation energy.
Yeah.
If energy of a particle is more than activation energy, then only it will react. So this is the activation energy point. Clear? Now we see that only a few number of particles are there which have energy more than the activation energy. Clear? So this only a few number of particles are there which have energy more than activation energy. And rest of them has low, all the particles there. These are the ones which have energy lower than that of the activation energy. Is that point clear?
Yeah.
Okay. Now, if you see, there are a number of features of Boltzmann distribution. No molecule have zero energy. No molecules have zero energy. The curve starts at the origin. Now, there are some features of this distribution. No molecule have zero energy. The curve starts at the origin. So the molecules do not have any zero energy, but the curve starts at the origin. The area under the curve, this area, the whole area, this whole area under the curve is equal to the total number of molecules. There is no maximum energy of a molecule. The curve does not meet at x-axis. Now this is x-axis. So there is no maximum energy because the curve is not meeting at the x-axis. The curve would need to reach infinity energy to meet the x-axis because it is something like this. Okay, it's not going to meet anywhere. So it will become almost parallel. So it will not going to meet. So it means no curve is having it means that no molecule is having a maximum amount of energy. Yeah.
Yeah.
Okay.
So will it not meet at one point?
Yeah, they are not going to meet. And you also see this point. This also it is not
But
going
if
to
it
meet.
keeps extending, would it not meet?
No, it will not meet. Na. It was saying there is no maximum energy of a molecule. This part is energy. So maximum energy means it should be something there. If it meets this point, then it will be the maximum energy. Clear?
Yeah.
This is the energy. If this line meet at, wait, I will delete this point. Suppose this curve is showing you the energy. Okay. Here,
Yeah.
this is line parallel this thing, and this will be parallel to it. It will be like this, parallel to it. It is not going to meet there. It is not going to meet like this. If it meets there, it means at this place, it means that there is the energy. You can calculate the energy at that point, but it is not meeting. So there is no energy of a molecule. There is no maximum energy for a molecule. The curve does not meet x-axis at high energy. The curve need to reach infinite energy to meet the x-axis, or you can say to meet the energy. It will meet at infinity. Infinity means it is not going to meet. Is that point clear?
Yeah.
So all these 3 points are clear. These are the number of main features of Boltzmann distribution.
Yeah.
Okay. Okay. Now we have the Boltzmann distribution and temperature. The effect of temperature on a Boltzmann distribution curve is shown in figure 2. Now we will see figure 2. Now this is a T1 and this is a T2. Now, if you see in the T1 case, activation energy is low. In this case, activation energy is high. It means at higher temperature, activation energy T2 has a greater portion of molecules that can overcome the activation energy. Now, if you see this area, blue portion, this is very less, and in this area, this blue plus red is very, very high. It means as the temperature increases, it means more number of particles can overcome the activation energy. It means more easy the distribution. Clear?
Yeah.
Okay. So the second thing what you can observe at the highest temperature, if temperature is high, at the higher temperature T2, the peak is lower and shifted to right. This peak is lower at temperature T1, the peak is this one, and the peak is lower, but it is shifted towards the right. It means more number of particles are having that much amount of temperature regarding this thing. In this case, only this temperature, the number of particles is this one, but here the number of particles is different. The energy is totally different. Clear? If I match this peak with that point, means at this point, and sorry, and if I need this, and we meet this. Now what you are getting it. At this point, just a minute. Okay, if you see at this point, the energy and the number of particles and energy and number of particles. Here the energy is less, here the energy is less, here the energy is more. So more number of particles are having that much amount of energy, less number of particles. The number of particles is same, but they are having different amount of energy. As the temperature changes, the energy is different. Here?
Yeah.
Okay, that is what I am trying to show you. I will delete all these. So what it is saying, as the temperature increases, the average energy of the molecules also increases. Now, if you increase the temperature, the average energy will also increase because temperature is directly proportional to kinetic energy. Whereas the kinetic energy increases, temperature increases. Here, now, a small portion molecule will still have low energy. A small portion molecules will still have low energy, but more molecules have high energy. More molecules will have high energy. The graph now stretched over a greater range of energy level. Is that point clear?
Yeah.
The small portion molecules will still have lower energy, but more molecules have high energy. The graph now stretched over a greater range of energy values. The peak of a graph is shown on y-axis and further along the x-axis. This peak, this peak is different. This is on T1 and T2. The peak is totally different. Now what is saying, the graph is now stretched over a greater range of energy values. The peak of the graph is lowered on y-axis and further along the x-axis. It's lower, this is y-axis and this one is the x-axis. So it is lower on the y-axis and it is farther along the x-axis. And the peak at the high energy, and the peak is at the high energy. Peak is towards the high energy, high amount of energy. It means more number of particles are having high amount of energy. The number of molecules is same, so the area under the curve remains same. Now, as the number of molecules are same, so area under the curve remains same in this case. Here?
Yeah.
Now at high temperature, more molecules have energy greater than or equal to the activation energy. You can clearly see this area. This area is when has been increased. It means at high temperature, more number of particles are there which have a greater amount of energy, that is more than the activation energy. Therefore, if activation energy is more, it means it is a greater probability of collisions which lead to the reaction and increasing the rate of reaction. That point clear?
Yeah.
As the number of particles which are having energy more than that of the activation energy, it will create more collision. More collision means there are chances that the rate of reaction will move faster. Rate of reaction will be faster. The next point is collision will also be more frequent as the molecule are moving faster. Now collision will be more frequent as the molecules. Now as the activation energy is increased, more temperature is there, more kinetic energy. More kinetic energy means now the particles are going to move faster. They will move here and there quickly. Now, as they are moving here and there quickly, what will happen? The increased energy of the molecules is much more important than the increased frequency of collision, which increases the collisions will also be more frequent. The more frequently it will collide. As the molecules are moving faster, but the increased energy of molecules is much more important. The energy of the molecules is now very, very high. And because of this thing, their frequency is also increased and there can be a perfect collision so that the reaction can happen. Is that point clear?
Yeah.
Okay. So we can say that increasing energy of a collision is much more important than the increased frequency of the collision. Collision frequency can be increased, but this collision is not having that much amount of energy, then it is not of any use. Clear?
Yeah.
But it should have the energy more than activation energy. Okay. I think it's finished. That's your last paragraph. Now, the Boltzmann distribution and catalyst. In figure 10.2, in topic 10.2 earlier, you learned that the catalyst lowers down the activation. In the previous chapter, we stated that the catalyst lowers down the activation energy of a reaction. The effect of catalyst on the activation energy is shown in the Boltzmann distribution. Now see, this is the Boltzmann distribution. Now this EA is without catalyst, and as you add the catalyst, the energy is lowered down. So now this is now become EA with the catalyst. Now as this is the EA with the catalyst, you can clearly see more number of particles there. As the number of particles are more, which have more energy than the activation energy, it means there will be more rate of reaction. So reaction will increase. Clear?
Yeah.
Any doubt in this? Any doubt better in this?
Just 1 second.
Got it?
Yeah. Yeah.
Okay. Okay then. Then we have okay, now see, a catalyst provides an alternate reaction route with the lower activation energy, that is EC on that graph, compared to EA, a greater proportion of a molecule now have an energy equal to or greater than to the activation energy. Now see, now compared to EA, if you're comparing with this EA, a greater portion of molecules now have an energy equal to or greater than the lower activation energy. As the activation energy is lowered, it means that the more number of particles are having the energy which is more than activation energy. It means on collision, more molecules will react to form product, and which as a result, there is an increase in rate of reaction. Clear? As a result, there is an increase in rate of reaction. Okay, so this is all about Boltzmann distribution. Here, these graphs you need to remember about the Boltzmann distribution graphs. Okay, so now you have these 3 questions. You will do these 3 questions. Okay, before that, should you want to start with this or you want to do question? Okay, do one
Start
thing.
this.
Okay, do one thing. Quickly do these questions, then we will do rest part.
Can
Quickly
I
do
do that later? Because I feel like they waste the.
Okay, so now we are going to start with our 10.4 dynamic equilibrium and Chatelier principle. Okay, now dynamic equilibrium is said to be dynamic in nature. Now dynamic means that is in the motion. Now what is happening? Suppose there is an equilibrium between A and B. What does it mean? It means the A is converting into B and B is converting into A. So we see that the concentration of both A and B are seems to be same, but the rate of changing of B to A and A to B and B to A seems to be same, but internally it is moving. Moving means internally the reaction is going on. There is nothing like that reaction of rate of reaction is stopped. The reaction is stopped. Reaction always in the motion. So that's why we call it as a dynamic equilibrium. Okay. Now, Chatelier principle is again a principle which tells us about the changes, how the equilibrium shifts whenever there is a change. So we will discuss Chatelier principle in detail. Now, first of all, we have introducing the reversible reaction. Now, reversible means that can be reversed. In a reaction, suppose we have a reactant. So reactant react and form a product. This is a one-way reaction. Okay, that reaction is not a reversible, that is irreversible reaction. So reactant can convert into a product and it will not change. For example, making of chapati making जो रोटी बनाते हैं, that is a formation, bread making or chapati making, this is a irreversible reaction. You can't again make dough from it. But if suppose there is a reaction in which product can again be converted into a reactant, then we call it as a reversible reaction. Here, so reversible reactions are those reactions in which reactant converts into product and product can again be converted into reactant. Okay. Now, when ignited, hydrogen reacts with oxygen and forms the oxygens in the air to form water. That is H2 plus O2 gives you H2O. At the end of the reaction, all the hydrogen has been used up and the reaction has gone to completion. The equation shows an arrow pointing towards the reaction, that is this one, which is describing the whole process. That is 2 H2 plus O2 gives you twice H2O. Reactants are hydrogen and oxygen, and we got a product of water. Now, in this topic, you will look at some irreversible reaction. So you look at some irreversible reaction. Now, reactions that takes place in both forward as well as reverse direction. Forward direction means this way, reversal direction means this way. If reactant are converting into product, this is a forward direction. If product is converting into reactant, it is supposed to be a reversible direction. So those reactions in which both forward and reversible direction occur is known as a reversible reaction. So many of these reactions are important in industrial processes. For example, in the Haber's process. Haber's process is for the manufacturing of ammonia. We have nitrogen and hydrogen. They combine together and form ammonia. So as soon as nitrogen and hydrogen combine together, we need to remove this ammonia from a container. Otherwise, this NH3, that ammonia formed, will again dissociate into N2 and H2. So it is not of any use. If you see in this case, we have a different symbol. If you see this symbol, this is something like this. So this symbol is representing the reversible reaction. This symbol that towards both the arrows, in this symbol, the arrows are half arrow is towards the reactant, half arrow is towards the product. So this is known as a reversible reaction, and it is in equilibrium. Equilibrium means that the rate of forward reaction is equal to rate of backward reaction. Is that point clear?
Yeah.
Okay. Now dynamic equilibrium. In an equilibrium system, the rate of forward reaction is equal to the rate of reverse reaction, and the concentration of the reactant and the product do not change. The concentration remains change in the case of equilibrium, and rate is equal to forward rate is equal to backward rate. So equilibrium systems are dynamic. At equilibrium, both the forward and the reversible reactions are taking place. At equilibrium, both forward and reversible reactions are taking place. As fast as the reactants are becoming product. As fast as the reactants are becoming product, the products are reacting and becoming the reactant. The products are reacting and becoming the reactant again. I'm telling you, equilibrium systems are dynamic in nature. At equilibrium, both the forward and the reverse reactions are taking place. It is going forward and it's going reverse also. And as the reactants are becoming product, as these reactants are becoming product, the product are reacting to become reactant. In this case, nitrogen and hydrogen are reacting with each other and producing ammonia. And ammonia again dissociates into nitrogen and hydrogen, giving you the reactants back. Therefore, in an equilibrium system, the concentration of reactant and product remain unchanged. This concentration of all these three remain unchanged, even though the forward and reverse reactions are still taking place. Even though reaction is taking place, but their concentration is not changing. Wherever there is a reaction, it means the rate of concentration should increase or decrease. The concentration should increase or decrease. There should be a change in concentration. But at equilibrium, the change in concentration is not observed. It looks like it is a standstill, but reaction is still going on. That is why we call it as a dynamic in nature. So for a reaction to remain in equilibrium, the system must be closed. Now this reaction, if this reaction is happening in a closed system, then it is a reversible reaction. If this reaction is not happening in a closed system, then what will happen? As soon as this ammonia is produced, it will move out, and as it move out, it will not again give you N2 and H3, N2 and H2. So whenever you need a reversible, whenever you need to, you can say you want equilibrium, that equilibrium must be done in a closed system. A closed system is isolated from the surrounding. So the temperature, pressure, and concentration of the reactant in the product are unaffected by the outside influences. So a closed system is a system which is a little bit cut from the outside. This isolation from its surrounding. There is no change of, you can say, temperature, pressure, and concentration. So no change, no exchange of matter takes place basically in it. Clear?
Yeah.
Any doubt in this?
No.
Okay. Then we have Lee-Chatelier principle. Now Lee-Chatelier is a scientist and he gave a principle. Now, for example, suppose uh, if someone hits you, so what you will do? You will again hit him. If there is a fight between you and your sister, so if she pushes you, you will also push her. Yes or no?
Yeah.
Okay. It means
Yeah.
whatever the changes are there externally in you, you tend to move yourself in such a way that you will try to mitigate that particular change. Clear?
So
This is also
you
you're
have
not
to
getting it.
give
Okay.
the same amount.
No,
Like,
not give the same amount. It is like that. Suppose you are in equilibrium. Okay.
yeah.
Okay. And there is a change from the external change. So now this equilibrium will shift itself so that it will undo the equilibrium, undo the change. Now, whenever suppose a system is going on, suppose there is a change. Now, this equilibrium will change itself in such a way that it will readjust or it will, you can say, minimize the effect of change. Is that point clear? Yes or no? Am I audible? Manya? Okay, am I audible?
Yeah.
Okay, fine. See. Now, Lee-Chatelier principle, the main principle or the main objective of this principle is that whenever a system is in equilibrium and there is any external change, then the system will try to readjust itself in such a way that it will minimize the effect of change. Now, suppose, for example, you are eating some food. If in this food you have a more amount of salt, now what you will do? You will try to minimize that salt. You will add some amount of, you can say, water in it. You will dilute it, or you will add some sort of milk in it into it. Yes or no?
Yeah.
You will
Yeah.
try to dilute it. You will try to, suppose by mistake, okay, suppose you by mistake you add some more salt, so your equilibrium is disturbed. So you will now add in the system something like that. It will minimize the particular change. So that is again in the case of chemical reaction. Same thing is in the chemical reaction. The position of equilibrium indicates the extent of reaction. In a reversible reaction, if the temperature, pressure, or the concentration of the reactant or product is changed, then the position of the equilibrium is changed. Now suppose A to B, a reaction is going on, which is a reversible reaction. Now this reaction is having a specific temperature, it is having a specific, you can say, pressure. Everything is fixed in that case. For A and B, everything is fixed, temperature, pressure, and this concentration is fixed. Now suppose somehow if I add more amount of A, that is reactant are added more, then what will happen? The more amount of B's will be produced. It means the reaction will shift towards the forward direction.
Yeah.
Yes. So that is
Yeah.
what I am asking, that whenever there is a change in anything, the reaction or the equilibrium will shift it towards in a position so that it can nullify the change. So Lee-Chatelier principle states that when a system is in equilibrium, is subjected to external change, is subjected to an external change, the system readjusts itself to minimize the effect of that change. It will readjust itself such that this change will be minimized. The effect will be minimized. Clear?
Yeah.
Any doubt in this?
No. Mm.
Got it?
No. Yeah.
Okay. Now see. Now figure 1 will explain you better. Now suppose this is an equilibrium. So there are 3 dots and these 2 dots are there. It is an equilibrium. Now as you put one more dot in there, what will happen? The system will be there. Clear?
Yeah.
If you remove this dot, it will again be in equilibrium. If you remove this and add one more there, the system is readjusted. Clear?
Yeah.
So this is the case that whenever there is a disturbance in equilibrium, then the shift system will try to readjust itself. Okay. Now see, a system which is in equilibrium has been disturbed by adding more reactant in the molecule. The more reactant in the molecules are there. The position of the equilibrium shifts towards the right. It will shift towards the right of the equation. The more products are made than the reactant until the new equilibrium is established. Now what will happen? These reactants will try to make more number of products. So you can see now there are 4 more number of products are there. So again it will be in equilibrium. Clear?
Yeah.
So okay, fine. Any doubt in this case?
No, yeah, I get
It
that
means
bit.
as the concentration of reactant increases, the equilibrium will shift towards the forward direction. Always remember that. And if the concentration of product increases, the equilibrium will shift towards the backward direction. Okay. If the concentration of reactant decreases, then again the equilibrium will shift towards the backward direction. So that the concentration will become, so that the equilibrium will be maintained. Now the effect of concentration changes on the equilibrium. See, the changing the concentration of a reactant or a product in the equilibrium system will change the rate of forward and reverse reaction. Here, as
Yeah.
the concentration of a reactant or a product in an equilibrium changes, the rate of forward and the reverse reaction also changes. The position of equilibrium will then changes. Figure 2. Figure 2. This figure 2 shows the effect of change of concentration of reactant or product. Now see, when an equilibrium system adjusted as a result of the change, if more number of product form, the position of equilibrium shifted towards the right. If there are more reactant formed, then the positions are shifted towards the left. Remember that when the product are there, product are shifting towards the right, and when the reactants are moved, it will shift towards the left. Now see, A plus B gives you C plus D. Clear?
Yeah.
If you increase the concentration of reactant, increase the concentration of A and B, then it will shift towards the reactant side this way. Okay. Or if there is a decrease in the concentration of C plus D, then again it will shift in that direction. Which direction? Forward direction. Clear? Is that point clear?
Yeah.
Now increase in the concentration of C and D. If this is the concentration of C and D is increased, it will move towards the reactant side. And if there's a decrease in concentration of C and B, it will again move to the reactant side. Okay. So if you choose equilibrium where the reactant and the product have different colors, simple experiments can illustrate how the position of the equilibrium changes with an external change. It can be shown if you have, you can say if there is any color change during a particular chemical reaction, it can be easily shown that how this particular thing is changing. Here,
Yeah.
or this can be investigated. This can be done with the help of chromium thing. Chromium. Now, if you see, chromium is yellow in color. Okay. Now see, the equilibrium between the aqueous chromium ions or chromate ions, that is Cr2, Cr4 minus 2, and dichromate ion Cr2O7 is sensitive to change in the acid concentration. The solution of chromate and dichromate ions have different colors, so it is easy to see whether there is any change in the position of equilibrium or not. Now, if there is a chromate ion, yellow color, yellow in color, if you add any H hydrogen into it, H positive ion, so what will happen? It will convert into orange color. Clear? It will convert into
Yeah.
okay. Got it? Is
Yeah.
that
Got
clear?
it.
Any doubt in this?
No. No.
Hmm?
No. No.
Okay. Fine. Now looking at figure 3, would you accept the position of the equilibrium would change by the altering the concentration of the reactant or the product? Now you can try the simple.
Sir,
Yes.
can we stop it here because we haven't done this yet in school?
Okay,
Like
fine. Okay, fine. We
we
will just finish this
haven't.
thing. Just finish this point. Then we will do. Okay. Then we will finish.
Yeah.
Just we will finish this particular thing. What this Lee Chatelier is going on. Okay. Now, if you look at this figure 3, you would expect that the position of equilibrium would be changed by altering the concentration of the reactant or the product. Now, concentration of reactant or product. Now, concentration of reactant is this one. If there are more amount of Cr2O4, if I add more amount of Cr2O4 into it, what will happen? It will again convert it to yellow color. Okay, this will change. Now see
Yeah.
this side. Now add a solution of yellow potassium chromate K2Cr2O4 to a beaker. You can do this experiment by yourself. Add more amount of yellow potassium chromate in the beaker. Then add a dilute sulfuric acid H2SO4 dropwise until there is no further change. The solution turns an orange color. Now add aqueous sodium hydroxide until it is no further change. The solution turns black or yellow color. Clear? So this experiment you can do. You can repeat step 2 and 3 many times and color will change each time from yellow to orange to black and yellow again. So this is how it will work. So when you add this dilute H2SO4, you are increasing the concentration of H positive ion. As the concentration of H positive ion increases, it will move towards the orange side. Clear? As the concentration of this H positive ion increases, it will move towards orange side. And if you add NaOH in it, NaOH in it, what will happen? It will again convert to yellow side.
Yeah. Yeah.
So in this way, you can increase or decrease this thing so many times. And you can clearly see the difference how the rate of concentration of reactant, if the concentration of reactant is increased, it will move towards the product side. If the concentration of product is increased, it will move towards the reactant side. Here,
Yeah.
that is what they are saying. When you add dilute sulfuric acid, you are increasing the concentration of H positive ion. And this increases the rate of forward reaction. And so the position of equilibrium is shifted to minimize the change in H positive ion. So as the concentration shifted towards the product side, they want to minimize the change. So the shift decreases the concentration of the added reactant H positive ion. So what actually they are doing, the shift is trying to reduce the concentration of H positive ion. The position in equilibrium shifts towards the right of the equation, making more product. And third point, a new position of equilibrium is established towards the product. And in that case, a new position will be there. And the solution will turn yellow, which is telling us about the shifting of equilibrium. Now again, if you are adding NaOH, what will happen? You are now adding the more number of reactant or product. Now this NaOH added OH negative ion. It reacts with the H positive ion. Now decrease in the concentration of H positive ion. Now what is happening? If you add NaOH ion there, this OH negative ion will react with H positive ion. It means the concentration of H positive ion will decrease. Clear? As the concentration of H positive ion will decrease, what will happen? This orange color will move towards the yellow. Clear?
Yeah.
Sure hai pakka?
Yeah.
So, okay, now see, acid add yellow to orange, base add orange to yellow. So the position of equilibrium shifts towards the left, making more H positive ion reactant, and the new position of equilibrium will be established. The solution turns yellow as CrO4 minus 2 aqueous form, and which is summarized in that particular equation. Clear?
Yeah.
Fine. Okay, so this is all about how the concentration is changing the Lee Chatelier equilibrium. Lee Chatelier principle is explaining how the change in concentration will change the concentration of change the equilibrium, and how the rate of reaction will be affected, how the equilibrium will be shifted. Now in next class we will discuss about the equilibrium of temperature, okay, and other things.